Good afternoon, ladies and gentlemen, and welcome to this clip where we will look at modeling wind loads on a billboard in Prokon SUMO module. My name is Jacobus Oberholster. I'm an AEC and Prokon technical consultant with Micrographics, and you can see my email address in the bottom left there. You are welcome to reach out at any stage if you have any queries or if there's anything specific you'd like to see. I really would encourage you to like and subscribe to our channel, to like this video specifically and others, of course, and to leave a comment if there's anything specific you are interested in. This clip was actually inspired by a comment from one of our viewers. So without further ado, let's jump into this exciting clip. So here we have our billboard model and just some of the details I'd like to show you. So for one, it's our paired footing or our foundation. You can see that the stub column is rounded, and that is set up over here by making the height value of the stub 0, and then that width value becomes the diameter of that stub. We've got a base plate as well. Don't stress too much about what it looks like visually. We do set up the geometry and so forth as accurately as possible because that just makes it a lot easier to design it once we export it to the base plate design module using the base plate design link. Now, of course, what that link records is the column geometry, that of the base plate as well. And of course, most importantly, it records the imposed loads on that particular base plate, which really just streamlines the process of designing that base plate. We've got our nice big circular column over here. So it's a 508 by 16. And then we've got the interface between that column and these supporting beams as a plain shell. So if we look at that plain shell, it's a 20 mil thick plate with a mesh of 0.1 and the assigned material is 350W, and that is something that we will be looking at in our clip for today as well. Then we've got our billboard over here, so a lattice structure of angles, and then of course with these I-beams at the bottom. We've got a live load, so that's quite a large live load, so 1.5 kilonewtons per meter, and that's just to simulate if the guys are actually hanging something off of this or walking on top of the structure, etc. You might know more accurate values, but this is just to simulate some of the loads on this structure. We've also got a dead load for self-weight. I'm not going to add anything else over there. And then lastly, we've got our wind load. All right, so before we get to assigning our wind load, what I want to take us through is just the process of running the simulation and looking at some of the difficulties you might encounter, especially with this column to, let's say, billboard interface. If you want to simulate this as a thick steel plate, otherwise you can also just have a crisscross of rigid links. Also, that's also totally acceptable. It might be a simpler way of doing this, but in this specific regard, let's just have a look. Maybe you can even model in gussets using plain shells, etc. Just depends on how accurate you want this model to be. So, all right. So what I'm going to do is I'm going to go to analysis and settings. For now, I'm going to keep it as a linear analysis type, just because I want to identify any anomalies in the model without running a more complex analysis type, which will take longer to run. So I'm going to solve, I'm going to save, and I'm going to go to results. And then everything actually seems fine. We don't have any abnormalities in terms of any of the members that haven't been connected properly. Everything seems fine. I actually do need to add some segments to this column, and we'll chat about that shortly. But we can see here that there's quite a bit of deflection at this location over here. So it really depends on you as to what you are looking to design, specifically with this interface over here. What I want is just a distribution of the forces from the structure into the column. All right, so I'm not interested in designing this plate. So what I'm going to do is I'm going to go back. I'm going to select that plate. Let's see if I can select it. And I'm going to modify some of these stiffness values. So you can click on them. You see there's a membrane stiffness modification factor in different directions. and there's the bending stiffness modification factor. So I'm going to change this value to 5, so dxx and dyyy to 5, and what we want is we just want a stiffer plate. So I'm going to run the analysis again. Let's have a look. Has anything changed? We can see yes, our deflection is actually a third of what it was. So I might go and increase this value even more. So I'm going to make it 10 and 10. Remember, I'm not looking to design this plate, and I just want the forces to be transferred from this superstructure to the column. Remember, you must always be cognizant of changing any sort of stiffness parameters, as it does affect the model. And we can see there we're at 1.35 and 1.58. All right, so I'm happy with that for now. So I'm going to go back now, and what I'm going to do is I'm going to add a wind load to the face of this lattice structure. So I'm going to go to loads, click on wind first. I'm going to set the appropriate code. So you can see there are a few to choose from. I'm going to go for the latest SANS code. Return period of 50 years is good. And my fundamental basic wind speed, which I can read off of that map in the code, I'm going to set to 40. I'm happy with the terrain category of A and a topography factor of 1. And the site altitude can remain as is. And I'm going to click OK. Now I'm going to click on wind, and I'm going to define this area over here. Just making sure I select that corner. I've closed the loop. I've hit accept, and we can see the pressure is now on the inside. So what I can do is I can select this wind load, and in its properties panel, I can click on flip direction. So I'm going to click flip direction. And now we see that we've got some errors here at the bottom. So it says that elements are not allowed to intersect, remove intersecting elements using the wind loading members dialog. The wind load is not being transferred to load bearing elements, etc., etc. So there are some limitations with regards to this specific tool. So one of them is that you can see it applies a uniform pressure. So in the case where you may be looking at zones or anything like that, this tool, or rather you'd have to define multiple of these perimeters. All right, so one perimeter for one wind load will have a uniform pressure over that entire area. You can change some of the CP net values. You can say use uniform wind pressure. So if we turn that off, nothing has, oh, it did change actually a little bit. And I do believe that that is more so looking at the reference height. So we can see here, once we click on it, it says use uniform wind pressure. It says apply the wind pressure uniformly over the area. The maximum height Y is used as the wind reference height to calculate the wind pressure. If not selected, the pressure will be integrated over the surface varying with height. All right, so it just has to do with the height. Okay, if we say use uniform wind pressure, we get the highest reference height dictates the magnitude of this pressure. All right, so say for instance you didn't notice, or you're not really sure how to check now whether you fixed this problem with the wind loading, with the wind load, is when you go to the discretized model view, so that's up here, you want to see that this wind load has been assigned to specific elements. So basically, using the tributary widths, etc., or tributary areas, this area load should be reduced to a series of line loads on the respective members. If you go to the discretized model view and it still looks like an area load, it means that this wind load is not being applied properly, and you'll have an error when you run the analysis. So the rule here is, let me actually turn off the live loads. The rule here is that the wind load should either be applied to vertical members or to horizontal members. All right, let's not overcomplicate it, and let's use that as the rule. All right, so vertical or horizontal, not both vertical and horizontal. So it might require, I'm not sure whether you can actually put two of these on top of each other. I've never tried to do that. Let's actually have a quick look. Is that something that we can do? It might just say that we've got two up on top of each other. Okay, that's fine. It's all the same. Let's see if we can flip this direction. Okay, so it's not creating an error at the moment, but it might. All right, so that's just something to remain cognizant of, that you could set it up in such a way that you have the one wind load applies to the horizontal members and the other one to the vertical members. All right, it'll just take a bit of experimentation. But let's get this one working. So we're going to select it. I'm going to go down into its property palettes and I'm going to look for loaded elements, and I'm going to click on that button over there. All right, so these are loaded elements on the left and removed elements on the right. So what I'm going to look for is with the beam numbers, if I click on them, rather if I go to the volumetric view, it highlights that particular beam. All right, so I don't want these braces. If I look at beam 7, we can see that beam 7 is vertical, so I'm going to keep those guys. And then let's see, beam 84, no, and beam 9. Okay, so the beam 9s and the beam 7s are the ones I want. So I'm going to select the rest of these. I'm going to throw them out, and you can see that sometimes it's clever and it immediately picks up once you've removed one set of these elements. All right, these are the elements that this should now be applied to. So you have got beam 7, you can see there, and the reason why these are separate is because they've got different orientations. You can see there that the face is inwards to let's say to the right, and this faces inwards to the left. So now we can say OK. And if we go to the discretized model view now, you see that it's now been distributed, or it's being distributed to those vertical members. All right, so let's try copying this wind load. So I'm going to copy it and place it again. I'm going to select one of them, and I'm going to change the loaded elements. All right, so let's see which of these guys. That is a beam 8. All right, so we're going to go for beam 8. You can see that there are 4 of them. There we go. Beam 1. Going to take that guy out and take that guy out. And let's see, there's beam 1 and the 4 beam 8s. Let's say OK. And it does seem to work. All right, that's great. That's new for me as well. I've never tried to impose them over one another. The only thing to be cognizant of here is the magnitude of this pressure, because you've now got double that over that area. So that is just something to keep track of. All right, so for this particular scenario, I'm going to delete one of them. But you are now, or I hope that you are now confident in how to apply that wind load. All right, so we've just got one more error. It says plane shell must be meshed. That's all good and well. I'm going to mesh it. I'm going to save my model. I'm going to run the linear analysis first, just again to check for any anomalies. Let's run that one. Okay, it says elements which started inside the defined area have been removed. That's all good. Go to results, and let's have a quick look at our wind. All right. It's not perfect as it is. I'm going to go back. I'm going to select my column and add some segments. I'm going to run the analysis. And let's look. We can see that that looks a little bit better. Okay, that's quite a large displacement, I must say. But we see that the model acts correctly. All right, again, I think this plain shell can cause some difficulties here. So what I'm going to do is I'm just going to remove it and place into rigid links. And let's have a look at how that works. So I'm going to go insert, or sorry, rather structure, rigid links. There we go. And a rigid link over there. I can even add more than that. But let's see. Let's see for now what's going to happen. Let's run the analysis. And we can actually see that that behaves way more normally, to me at least. And we see that our deflections are down quite a bit in terms of the maximum Y deflection. All right, now we have our load combination. So we do have that there. So what I'm going to do now is I'm going to run a second order, and we might actually have a failure here. Let's see. We might have a failure. All right, so no failure, which means that no elements are buckling in this model. But there we go. And of course, this deflection is incredibly high. So there's some modifications we need to make to this model and so forth. But I think that has been run successfully. All right, so I hope you found that interesting. If you have any questions, please pop them in the comment sections below. What I will do in the next clip is I will just be running through the process of designing the base plate and then the pad footing as well. So please look out for the next videos that will be released shortly. Thank you so much for tuning in. Please like the video, subscribe to our channel, and if there's anything specifically you'd like to see, please pop it in the comment sections below. Like I mentioned, this clip was inspired by a comment from one of our viewers. So thank you so much again, and hope that you have an awesome afternoon and week further.